Hi there, welcome to your lesson on quadratics in intercept form. If you're ever bored at the beach, consider doing some quadratics in the sand. It's always good fun. Alright, let's recap. We have three forms of quadratics. One is called the standard form, one is called the vertex form, and one is called the intercept or factored form. In the last video, well, we've been dealing with standard form for a while now. You should be familiar with those. In the recent video, we looked at vertex form. Now you should understand that h and k represent the x and y values of the vertex. And finally, a has the same effect in both of those. There's an a in front here, a in front here. That a determines the width of the parabola and whether it is concave up or concave down. In this video, we'll look in more detail on intercept form quadratics, which we've looked at in a way because we've always been taking standard form, factoring them, and creating this form. So this form is sometimes called factored form. We're going to look at it in more detail today. We're going to begin with an exploration this time as well. For this exploration, you do not need Desmos as you did before. This one, you just need some paper and some mental stamina. You're going to do 6 graphing problems, so it might take a few minutes. Definitely have your notebook and a pen ready. Don't quit. When things like this come up, you got to investigate fully. Take advantage of the practice opportunity you have here to really master your work with quadratics. Let's try. Let's get started. Okay, so what we have is 3 quadratics given in standard form. For each, you are to do steps 1 through 4, and then graph it. Steps 1 through 4 are finding the y-intercept, finding the vertex, then changing it to intercept form by factoring, and then finding the x-intercepts. You're going to do 3 like this. You're going to do 3 more that are slightly different than these, you'll see. And then you're going to make a conclusion about what happened. What happened when we graphed these? What happened when we graphed the other ones? And you're going to see something interesting occur. So let's get started on this. First one, let's graph it. First step is, what is the y-intercept? Well, we know the y-intercept is determined by the c value here, so our y-intercept is 0, -6. Next, find the vertex. We know we can find the vertex using negative b over 2a, so negative b value is 1, so negative 1 over 2 times the 1 is negative 1 over 2, which is negative 0.5. Now to find the y value of the vertex, we can take this and substitute it back in here. You may need your calculator for this, so put negative 0.5 in here and here. Alright, the y value is negative 6.25. Therefore, our vertex is negative 0.5, negative 6.25. Next, we're going to change to intercept form by factoring. So take a look at that and factor it. Alright, factored form looks like that. So that is our intercept form. Notice there's no number in front. There's no a value. Well, there is. There's a 1. We don't see it, but there's a 1 there. And that 1 is our a value. We can see the 1 is here, and there's also a 1 here for the a, so the a values match. Okay, in intercept form, we can factor it. We can solve for x. When we solve for x, we are setting the y equal to 0, and then solving this by null factor law. We know x plus 3 equals 0, means x is negative 3, and x minus 2 is 0, which means x equals 2. Those two solutions in a graphical sense give us the x-intercepts. So that is why this form here, which we knew before is a factored form of a quadratic, that is why we call it intercept form when we were graphing, because those two values are our x-intercepts, so there they are. Alright, those x-intercepts help us graph, right? So here's the graph of that quadratic. Let's confirm all the points. Here's our vertex, negative 0.5, negative 6.25. Here's our y-intercept, 0, -6. And here's those two x-intercepts we found. Let's try the same thing for the next one here, the second quadratic. Okay, we're trying the second one now. So y-intercept, 0, 5. Vertex, using negative b over 2a, then substituting 2 into the equation, we get this vertex. Next, factor. In this case, I always recommend factoring a negative sign. I see a negative here, so I'm going to put a negative in front of the whole thing. When we were solving before we had 0 here, that negative could be eliminated, but we're going to keep the negative here because it still needs to be part of this equation. However, we can factor the part within the brackets here. That factors into x minus 5, x plus 1, and there's that negative that I kept in front here. So just like the standard form has that -1 a value, so does the intercept form. It has that -1 a value in front. So that a value has the same effect in terms of making it concave down and making it have a certain width. But here's the factors there. Those factors help us solve x-intercepts. So we set y equal to 0 to get x-intercepts. Now the negative is irrelevant because we can divide by -1. We can solve each of the two factors by setting equal to 0, and we get our x-intercepts in that way. Let's confirm the graph. Here it is. Vertex here matches what we had, y-intercept, and there's our two x-intercepts right there. And it is concave down as it should be. Next one, try the third one here. And in this one, I would suggest factoring out 2 first. Okay, y-intercept, -8. Let's see. Finding the vertex, 1.5 and 12.5 for the y, giving us this vertex. Again, we use -b over 2a to get that, and that was substituted back in here to get this. Next, factor it, and this is where I was saying factor out the 2 first. So the 2 has been factored out, makes this factoring here easier. That factors into these two factors. Now the 2 is our a value. Again, it's going to make the parabola narrower. It's concave up, and notice the 2 is here as our a value, and the 2 is here in our intercept form as well. So the a value remains in front of everything else, just like it did here. Alright, now those two factors allow us to solve, check your work here, and we get 2 x-intercepts. Let's check the graph and make sure. We can see, yes, it's a narrow parabola. We have a vertex here, we have a y-intercept here, and our 2 x-intercepts are here, the ones we found. Okay, so now our investigation continues. We've been looking at these parabolas and finding all the points and seeing what happens. The main conclusion here was that our factored form produces our x-intercepts, right? So now, look at these ones. They're going to be a little bit different. You'll see something different happen. We're going to go through the same process, but you'll see something different happen with these parabolas. Let's try. First one, all right, y-intercept 0, 9. Find the vertex. -b over 2a gives us -3. Put that back in here, and we get 0. Oh, interesting. Y is 0. We haven't seen that before. So that means our vertex is -3, 0. Next, we're going to factor it. That factors into this. Oh, also interesting. X plus 3 times x plus 3. If you may remember, this is called a perfect square trinomial. So we have this occurring twice. So that means we set it equals 0. That means we only have to solve for x once because they're identical. We get x equals -3. So what does that tell us about our x-intercepts? Well, there's only one, right? Because both of those will produce the same solutions. There's only one x-intercept, and that x-intercept is actually the same as the vertex. Very interesting. Therefore, we call this a double root, or a double zero. You'll see why on this graph. Let's take a look. Basically, this produces the same x-intercept, and an x-intercept is also called a root. So we call this a double root. Even though it happens once here, we still call it a double root. Alright, so we have our y-intercept here. We have our vertex here, which is also the x-intercept. So notice when we have this perfect square trinomial, the vertex ends up being the x-intercept. The parabola sits exactly at that perfect position where the vertex hits the axis. If you move this parabola a little bit lower, it would have 2 x-intercepts. If you move that higher, it would have no x-intercepts. But right now, at this perfect position, it has what's called a double root. The vertex is the x-intercept. Let's try with the next one. So try this one. Okay, y-intercept is 0, 4. Using -b over 2a, we get 2, 0 as our vertex. Again, we got 2, 0. Now, factors into this. Again, we see this common repeating factor. That means it's a perfect square, and it is. Solve it. We get x equals 2, and that means our x-intercept is 2, 0. Same thing happened as the first one. Our vertex is the x-intercept. And why is that? Because this is a perfect square trinomial. Here's a graph of this one, and you can see our double root. So here's our y-intercept, here's that double root, again sitting perfectly on the x-axis. Last one, try this one. Is this a perfect square? Maybe we see a pattern here. Okay, in this case, here's our y-intercept. Using negative b over 2a, we can solve that to get our vertex at negative 4, 0. Take out the negative, as I always suggest here. This can be easily factored then into x plus 4 times x plus 4. And solving, we get x plus 4 equals 0, x equals negative 4, telling us our x-intercept is at negative 4, 0. Check your work carefully. That is a double root once again. The graph shows us we have our vertex and x-intercept there. This time we had the negative in front here. So again, notice we had a negative 1a value here, means concave down, and we have a negative 1a value right here in front of the factored form as well. So concave down, there's our vertex, there's our y-intercept, and it sits perfectly on the axis. Vertex is the x-intercept because it is a perfect square trinomial. Double root or a double zero, repeating zero. Great, let's do some more things. So let's conclude some things from that. Reflections. The x-intercepts are also called zeros of a quadratic function y. Well, the x-intercepts are called the zeros because at the x-intercepts, the value of the y-coordinate is 0, and that's why we set y equal to 0 when we're solving for x. Consider the difference you saw between the first three and the next three. So the first three and the next three. And let's fill in the blanks. Quadratic equations will graph a parabola with a double zero when it is a perfect square trinomial. For these parabolas, the blank is also the blank. What goes in there? The vertex is also the x-intercept. We talked about that. We saw it. So based on this knowledge, look at the quadratics below and circle or highlight the ones that will have a vertex that is also the x-intercept. Which of these, in other words, will have double zeros? And let's call this number 1, number 2, number 3, and so on. All right, I hope you chose number 2, 3, 4, 6, and 7, because these are the ones that are all perfect square trinomials. Here we can see the double root clearly. Here we can also see a double root clearly, x plus 6 times x plus 6. This one also, x minus 4 times x minus 4. This one is a perfect square. This one is a perfect square. This one might look like a perfect square, but it is not because we have a minus sign. This one also may look like a perfect square, but it is not because of this minus sign here. Okay, some questions. All right, try this question. Now let's check our work. It says we want this in vertex form. So here's vertex form. I don't know a, h, or k yet. However, I do know the leading coefficient is 2, so I'm going to replace the a with 2. It tells us that. Next thing it tells us is the repeating 0 at negative 3. That means we have a vertex at negative 3, 0. Because if there's a repeating x-intercept, it means it's one of the situations where the x-intercept and the vertex are the same. So the vertex is the same as the x-intercept. So now I can plug those in for h and k for my vertex values, and I get this. And that can simplify to this. We can confirm that it's a perfect square trinomial by multiplying this out to become this, and we can see our perfect square trinomial there. So everything matches. Okay, important point, getting into decimals. You're going to look at this one. Here's a standard form. You want to flip it upside down, but keep the same x-intercepts. In decimals, you can investigate. Louisa argues that all you have to do is make the a value negative. So see how she put a negative in front right here, but everything else remained the same. So she knows that negative a will make it concave down. All right, Xavier argues you have to make the entire function negative. So he says take this whole thing, multiply everything by negative sign to change it to this. Check on decimals. Who's right? Who's wrong? Okay. Hopefully you notice Xavier is correct. You need to multiply everything by negative. So let's take a look. If you have a function like this, these are the same function, by the way. Intercept form, standard form. To flip it like this, but keep the same x-intercepts, notice they stay the same, negative 3 and 5, we need to make the whole function negative. This is a key point. We'll learn more about that in another unit, but for now, know that everything needs to be made negative. Okay, so that point is here, that a value influences which way a parabola opens and how wide it is. So with this parabola here, we're always going to have the same two x-intercepts, negative 2 and 4. But changing the a will change how the parabola is positioned or how wide it is, but the x-intercepts will remain the same. Challenge, try these. You can do it. I know you can.